Uh, Thanks to the organizers. So today I will talk about collective transport in hardcore run and tumble particles. There is a slight change in the title. So the presentation will be based on these two recent papers published this year, and this is in press. So transport on macroscopic scales is characterized through density and other parameter dependent transport coefficients. For example, you create density perturbation. So consider system with a single conserved quantity, which is a particle number or mass or something. So define it as density, satisfying detail balance. So now you create density perturbation, and then it relaxes through this coefficient, transport coefficient called bulk diffusion coefficient. Well, now once the perturbation is created, it relaxes. So the perturbation is created through fluctuations. So that's the through current fluctuation, and that is characterized through this transport coefficient chi. Both are density dependent, and it is interesting to note that even in equilibrium there is no rigorous proof. So this equation is set up rather through consistency condition, like through fluctuation dissipation theorems. So this is the white noise, satisfies this. Okay. So now what is the fluctuating hydrodynamics for systems violating detailed balance, such as self-propelled particles? Okay. So do the transport coefficient have singularities? Well, it can have. For example, our favorite Ising lattice gas, below some critical temperature, it phase separates. Kawasaki dynamics. So, well, there are clusterings. So at the critical point, it is characterized through the diffusion coefficient, which goes to 0. So it's called diffusive instability. Okay. So now what happens for the self-propelled particles? Well, in the past, in simulations, various simulations throughout past, I think, more than decades, people have observed that below some or above some critical activity, system phase separates. You get cluster state and dilute phase. Okay, collective, of course, density fluctuation. Well, so now there is a theory, and theory has uncanny similarity with that gas-liquid transition, which has a critical point where bulk diffusivity vanishes. So that's the theory. It is widely accepted. So now the question is that the case? Well, so it is a debatable issue, and in recent times, I will come to it, some of the references, that there are question mark on that theory. Let me be precise. I'm a bit provocative, but I would appreciate your comments in this regard. So I guess that, or I think, believe that there are no rigorous theoretical proof yet which will connect or indicate that bulk diffusivity indeed vanishes. Well, these are some reference. Closest are this one. They actually have calculated in a variant of conventional hardcore RTPs the bulk diffusivity in the leading order of gamma with the tumbling rate. This is one case. Kobir, I think, in the audience. Rajesh, I don't know. And Indranil. I see. Okay, fine. So then we calculate transport coefficients for hardcore random particles for arbitrary density and tumbling rate. So we implement an efficient numerical scheme to calculate this transport coefficient for one model. The other one, we developed an analytical scheme. So this is the model. So we know that run and tumble particles, the particle runs for certain distance or certain time. Once it hits the next particle, it just stops. So it has only two parameters in the system, which are density and tumbling rate, or in other words, persistence length. Okay. So during the persistence time, one could think of, so this is a variant. So this is not exactly the run and tumble particles. So during the persistence time, you can think of a model which has hardcore constraint, but it has long range hopping which mimics the ballistic motion of actual RTP or the standard RTPs. Well, that's the model here. So here this is a long range hopping model where hop lengths are drawn from a distribution which has a characteristic length scale of persistence length. Okay, so that's the model. And here one actually could do the calculation, and this is the result, exact result for bulk diffusion coefficient. So this one could write, it's a bit complicated, but you would concentrate that it depends on the gap distribution, right? So this is the in one dimension, and you could generalize this result to d dimension, any finite dimension, okay? And this is the expression for mobility, particle mobility or current fluctuation. And this depends on PG, but rather the second moment. The first one depends on the first moment of the gap distribution. So gap between two consecutive particles, right? Okay, so if you look into it more carefully, you see this is the first moment. So this is a nice quantity, right? So for a characteristic or say rather generic PG, one could show that D is bounded from below as well as above. So there is nothing interesting or no singularity in D rho. Okay, same with chi, the mobility, as long as rho and gamma is finite. Okay, so then what happens? So one could think, well, so this is actually physically one could understand this is because there is a finite length scale in the system. And when there is a finite length scale in the system, the D, the diffusivity, collective diffusion coefficient cannot vanish. Okay, so now what happens if you take, say, tumbling rate goes to infinity, sorry, 0. Well, so there are certain interesting things, and I would keep you guessing. So that would be probably story for next year. Okay, so is there nothing interesting? Well, no, there are some interesting things here. So, for example, the bulk diffusivity and the mobility, although there are two parameters, density and tumbling rate, this can be effectively expressed as the ratio between density and tumbling rate, and one could understand this simply because there are two length scales, which is persistence length and mean free path, which is actually 1 by rho, and that is the ratio, and that's why it in the small density and persistence limit, it has satisfied this scaling function, and we actually calculate this scaling function for the second model, the variant, as well as we calculate the current fluctuation. So this is the cumulative bond current up till time t, which also has a nice scaling function, which is this. So, well, this you can easily recognize the dimensionless variable. D is the diffusivity, dt by L square, so dimensionless. This one, so it requires some explanation. I'll do it probably later. Well, so next are the plots. I'll just flash it. So that's the basically end of the talk. So this is the scaling collapse of bulk diffusivity as a function of the scale variable rho by gamma, and you see that it's a nice scaling collapse for several decades, and the solid line is the analytically derived scaling function. Okay, so this is the usual RTP for which we do not could not calculate the scaling function, but we see the nice scaling collapse. Same with the particle mobility, where we have calculated the scaling function analytically, and the scale variable is this rho by gamma. Okay, and this one I'm not, this is in the paper. I mean, you could just refer to the paper or we could discuss later. So bulk diffusion coefficient and particle mobility for arbitrary density and tumbling rates have been calculated in two models of hardcore RTPs. We found a scaling law. Most importantly, there is no diffusive instability in the system. So the conclusion would be any finite dimension RTP class of model, there is no MIPS. So with that, I would like to thank you for your kind attention. Yes. Okay, nice question. Good question. Yes, we found it. And we actually show it analytically for the second one.
So in normal active matter systems, in the hydrodynamics, you'd find that two couple fields, usually the hydrodynamics is governed by two couple fields.
Yes.
Density and magnetization fields.
Okay.
But here it seems that your hydrodynamics is self-contained in only density fields.
Yes.
Right? Do you know why?
Yeah. This is because, this is precisely because the limit we consider. So there are two limits. One is gamma, which is tending to 0, right? And so that is the interesting limit we are interested in. Then there is another limit, L tending to infinity. So now it depends which one you take first. We first take the thermodynamic limit. So that's why the slow variable is the density, not the magnetization. So effectively you actually can integrate out magnetization. So that is the thing.
If there are no more questions, let us thank the speaker.